presentation in unit 2 entitled It's Just a Theory. It says the most exciting phrase to hear in science, the one that heralds new discoveries is not eureka, but that's funny. So the learning goals are that you be able to differentiate between a scientific hypothesis and a scientific theory, and that you be able to link the experimental observations to the atomic model. So what we already know. We already know from earlier grades that atoms are composed of protons, neutrons, and electrons, and that the interaction of these protons, neutrons, and electrons determines the properties of elements. So that's stuff that we already know. But how do we develop this model of protons, neutrons, and electrons? Now, you should know from the lab that there has been historically lots of different models of the atom and how they interact with light. There are multiple models, including the Dalton model, the Thomson model, the Rutherford model, and we stopped at the Bohr model. There are some further models that go beyond that, but for the purposes of this class, we're going to stick to these four. Now, ancient ideas. The very first idea for the atoms, or that where substances were composed of elements, and we call those elements air, earth, fire, and water. Okay, so for example, a stone may be 2 parts of earth, 1 part fire. And wood may be something that's 1 part earth, 1 part fire, and 1 part air, or something along those lines. So everything was a combination of these 4 elements. Democritus was an ancient Greek philosopher, and he was the first person to hypothesize, and it's a real key idea that he just said that a rock broken in half eventually gets to the point where it can no longer be broken in half. So a hypothesis is kind of an educated guess that's based on the evidence. Now here's the problem. This is not science. Okay, it's a great idea. It's a wonderful philosophical idea, but it is not science. But it is the origin of the term atomos. Atomos means indivisible. Okay, so the atom is the idea that you get to the point where something can no longer be divided. So Dalton was the first kind of scientific model of the atom. He hypothesized the same thing, that atoms are the basic building blocks of all substances. And so what he did is he mixed various amounts of gas to see what water was really composed of. He took some hydrogen gas, he took some oxygen gas, and he got water. He took some hydrogen gas, he took some oxygen gas, and he got water plus oxygen. He took some hydrogen, he took some oxygen, and he didn't get anything. So what he was able to show doing this is that atoms can be rearranged to form new substances, but there's a basic building block that he called the atom. He developed these postulates based on the evidence that he observed, that elements are small particles called atoms, and that all atoms of an element are the same. So this hydrogen atom and this hydrogen atom are the exact same. Okay, he also said that atoms can't be created, divided, or destroyed. So you have these 2 hydrogen atoms that could be connected. You can rearrange them. You can take this hydrogen and move it over here, but you can't totally wipe out the hydrogen. That's consistent with what we now know as the law of conservation of mass. He also said that atoms can combine to form whole number ratios. So for example, you can take 2 hydrogens and 1 oxygen and you can make H2O. But you can't take it and make H1.5O, because the 1.5, you can't take a half of an atom. So it's got to be in a whole number ratio. He also said that atoms can be combined, separated, and rearranged. So those are Dalton's 5 postulates that he observed based on the evidence. So using those postulates, he developed his model of the atom. Now, a model of the atom is what you think the atom is based on the available evidence and based on your conclusion. So he concluded that the atom is composed of elements, that it is indivisible and it's spherical. So you think of it almost like a marble or a bowling ball. It is a solid, indivisible sphere. Okay, a solid indivisible sphere. And that was what the atom was. So all atoms eventually get to the point where they're a solid indivisible sphere. Thomson came along and he thought Dalton's idea of an indivisible atom was incorrect. And he had lots of reasons for speculating on that, but the primary one is the idea of electricity. Okay, so scientists had been using electricity for quite a long time, over 100 years by the time Thomson came along, but they still didn't have a very good idea of what the origin of electricity was. Dalton thought it might have something to do with the structure of the atom, and so he hypothesized, okay, remember hypothesize is the guess, that atoms are made of different parts. And so he developed an experiment to test this. So once again, this is an idea. This is science because you have an experiment. So he designed an experiment to isolate the different parts and discover the electron. What he did is he kind of ran an electric current through an atom, and he was able to produce electricity. And in doing so, he said, well, the electricity had to come from somewhere, and he said it came from the atom. Based on that, he developed what is often referred to as the plum pudding or the chocolate chip cookie model. So he said that atoms are positive everywhere. They're always positive, except every once in a while they have these little chips. These little chips are the negative charges. And now we know those negative charges now are the electrons, but he hadn't actually named it at that point, so he called them negative corpuscles of charge, which are just a fancy way of saying it's a negative charge. So this was Thomson's model based on the evidence that he had developed. So if you look, as we're going through the atomic model, we had Dalton, and Dalton was great, but whenever new information came, we developed a new model based on our new information. So Rutherford came along, and his discovery was accidental. So this wasn't the idea that, oh, well, what I'm going to do is I'm going to test this principle because I think it's wrong. Rutherford actually had no idea what he was going to discover. In fact, he farmed this out to his grad students. Okay, he had two grad students, and they're also kind of famous in their own right, Geiger and Marsden. And he said, hey, I'm going to keep you guys busy with something, so why don't you go do this? And when he did that, they hypothesized that if you take an alpha particle is basically a helium nucleus, but it's just an alpha particle, and you fire it at gold foil, it should go straight through. They likened it to taking a cannon and firing it at Kleenex. And so they said, okay, it's just another thing for the grad student to do. Well, whenever they did this, they actually found an interesting result in that some of them got repelled. So imagine putting a piece of Kleenex in front of a cannon and firing it and having the cannonball go backwards. That was kind of the idea that they got here. So this was a completely accidental discovery. But Rutherford, based on these results, was able to take this idea and develop his model of the atom based on those results. This is often called the planetary model. Okay, it's called the planetary model because he discovered the nucleus. He said that there's a positive charge at the center of every atom, that it's not diffuse, it's not everywhere like it was in the Thomson model. There's a specific point that he called the nucleus that's the positive charge. He also said that the electrons must move around this positive charge. At this point, they all knew that opposites attract. So since they knew that opposites attract, they said, okay, these electrons must be moving in circles around the atoms. They can move in any direction. That's why they call this the planetary model. If you think of the nucleus as the sun and the electrons as planets, it's just simply the planets orbiting the sun. Now, with planets, you can be at any distance from the sun. That's why we have asteroids, we have asteroids at different distances from moving around the sun. So the electron position can vary depending on, I guess, how fast it's going and what its energy is at that point. Bohr came along and he thought Rutherford's idea of an electron that could move anywhere was wrong. And the reason why he had thought of this is it didn't make sense based on his observations of what he had seen with referring to light. So he hypothesized that electrons are limited to where they can move. Okay, he designed an experiment to examine the energy of electrons, and he discovered what's called the electron orbital. And what he did is he found that certain elements always give off certain colors of light. It will give off these colors of light every single time. And now that doesn't make any sense if the electron can be anywhere. If the electron can be anywhere, it would give off all colors of light. So Bohr developed what we now know as the Bohr model of the atom. Now this is the most common model that's used in chemistry. There is another model that has supplanted it, but is not relevant to this particular class. So the electrons orbit the nucleus, okay? But they orbit them at specific distances. The electron must be here, or it can be here, but it can't be in between. This in between is a no man's land. You can't have an electron that's in between orbitals. That's the whole idea of the Bohr model. So the electron has to be in an orbital. Whenever an electron absorbs energy, like if you shine a light on it, it causes the electron to jump up an orbital. Whenever the atom emits light, it causes the electron to move down an orbital. So Bohr's model not only explained the atom, the positive charge, the negative charge, it also explained how light interacts with an atom. So his is by far the most accurate model that we're going to talk about in this class. So if you think about it in terms of scientific progress, the first thing that people did is they had a hypothesis. And the hypothesis is often used as, hey, this is my guess. This is what I think is going to happen. My guess is as good as yours, but it's not. The hypothesis is based on prior experience and previous observations, previous models. Okay, it's not just a wild guess. It's a guess based on experience, based on previous models. So then you have the experiment. What did you do to test your idea? And this is what makes something science. It's the whole idea of empiricism. Empiricism is a fancy way of saying that you have to test your idea. Once you have an experiment, that experiment will yield results. Once you have the results, you are trying to explain the results using a theory. Okay, so you're saying, okay, every time I do this, I get the same colors of light produced. Why is that the case? Okay, a lot of times people get the idea of a theory and a law confused. The first thing is, you can never prove a theory correct. No matter how correct it is, all it takes is a single instance to disprove a theory. So you can never prove a theory absolutely, but you can disprove it. It's called falsifiability. A law is a simple, undeniable fact, like a rock dropped will fall. Okay, it's not an explanation. It doesn't say why it will fall. It just says, hey, this is going to happen. So you should be able to use hypothesis, experiment, theory, and laws correctly whenever you're doing your investigations. Okay, so match the scientists with their scientific discovery. Remember, the first one we had was Dalton, and he discovered the atom. The next one we had was Thomson, and he discovered the electron. Then Rutherford discovered the nucleus, and finally Bohr came in and he discovered the electron orbital. Next, developing A2, it says, which scientist had the most accurate model of the atom? It's Bohr. He was the one who included not only the nucleus, the electron, the nucleus, and the orbitals. Okay, would you classify the others as wrong? No. They were the best models available on their information. So it's like trying to say, hey, I'm going to give you a test over quantum mechanics tomorrow. And what you would say is, you say, I did the best that I could with the information that I had. I wasn't given the information that's on the test. So it's not necessarily wrong. It's the same basic idea. They did the best model they could with the information that was available. It says a student is conferring with their teacher about their grade. The teacher prevents evidence that the student can improve their grade by studying. The student leaves angry, saying, that's just a theory. What's wrong with the student's statement? Theories are well-grounded and established to be true. So a theory, whenever you say it's just a theory, you're showing that you don't understand the process of science itself. Whenever you say it's just a theory, okay, theory means it's well grounded, that it's established as being most likely true with the available information. The problem is the term theory is often connected to conspiracy. And so whenever you hear about a conspiracy theory, or was there a shooter on the grassy knoll for the JFK assassination, or did we really land on the moon, it discredits the word theory. The word theory means it's well established to be true. Finally, you have many scientists believe that atoms can be further broken down into strings of energy. Design an experiment to test this assertion. So the idea is you have protons. Here's the atom, and you have protons. If you were to take a proton and blow it up, it has quarks in it. Tiny, tiny, tiny particles called quarks. If you take a quark and you blow it up, the idea is eventually if you keep blowing it up, you get to the point where you have a vibrating string of energy. Now the question is to design an experiment to test this assertion. Now I'm not going to answer this question because if I did, I'd win a Nobel Prize. You can think about it and say, okay, well, how would I test this tiny assertion? If you're the person who develops an idea to test whether or not this tiny vibrating string of energy exists, there's a Nobel Prize and about $2 million in your future.